Hey, good morning. My name is Lance French, and I'm the Director of Marketing for W&M Environmental. And I'd like to welcome you to our webinar on vapor mitigation. Our speaker this morning is Frank Clark, Professional Engineer for W&M. Welcome, Frank.
Thank you, Lance.
Well, thank you for joining us today. We were going to get started really quickly, but at first I want to go over a few housekeeping items. First, we want your participation. There's a few interactive questions throughout the webinar, and we would love to get your answers. Also, if you have any questions throughout the webinar, please send them to me through the chat tab on your GoToWebinar dashboard. If by chance we don't get to your question, I will make sure Frank sees it, and we will get an answer to you as soon as possible. We will be recording this webinar, and it will be available to rewatch later this afternoon along with the slides that Frank uses, and I will send you an email with the link when they are made available. So let's get started. Frank, so this is our third webinar on vapor. The first webinar was about vapor intrusion and recent development. And then the second webinar the second webinar was about recent development and investigation. And this webinar is about vapor mitigation and how to address vapor mitigation problems. So we're going to briefly cover intrusion and investigation. So if you were here on the last vapor webinars, hang in there, we'll get to it. Okay, so that's enough out of me. Frank, it's all yours. Take it away.
Great. Thank you, Lance. Thank you, everyone, for attending this morning. As Lance mentioned, this is our third vapor intrusion webinar, so why are we spending so much time on this? We've really found that this is a very hot topic in our industry. The presence of vapor and vapor intrusion issues are now entering into the realm of many of the projects that we work on whenever there are volatile organic chemicals found on a piece of property. So it is a very hot topic. It's affecting real estate transactions. It's affecting investigation and closure of sites that are in regulatory programs. And the issue is now much more visible to regulators, in particular here in Texas, than even 12 or 24 months ago. So it is something that we are all dealing with on a daily basis here at W&M, and we wanted to share with you some of our experiences dealing with vapor intrusion and how it can be addressed on typical properties at least here in Texas. So first of all, what's the problem? In the late 1990s, people started to learn about vapor intrusion, particularly in the Northeast, where many buildings had basements and there were greater opportunities for contamination from nearby sites to enter into structures. The most common situation was a leaking underground gasoline tank that had a release that had affected groundwater. Vapors got into people's basements, and in extreme cases there was gasoline or strong gasoline vapors, which are very easy to detect, and in some cases even explosive situations. So that brought it to the forefront, and now we're many years further along, and we're realizing that those cases were extreme, but even low concentrations of volatile organic compounds into structures can cause health problems. So for purposes of this presentation, we're going to call vapor intrusion is the migration of volatile chemicals from contaminated soil and groundwater into an overlying building. In real estate transactions, many of you may have reviewed Phase 1 environmental reports. There is another term that's used in the industry called vapor encroachment. Encroachment is simply the presence of vapors on a property, which may be from a plume originating off-site. However, intrusion is really the next logical step. It's the migration of those vapors that have reached a property into a structure located on the property. That's what we'll be focusing on. The chemicals that we're concerned about, if you've been involved at all in environmental investigations or have had the unfortunate situation of having a Phase 2 or a site in the state's cleanup program, some of these will be familiar to you. The BTEX compounds are associated with gasoline and similar petroleum products. Trichloroethylene is a very common degreasing solvent. We now have found it I would say on 2/3 of the sites that we work on where we see organic contamination, TCE is one of the compounds that we see because it was a very common, very effective cleaning solvent for all types of material, in particular metal parts that might have been machined and used in manufacturing. Tetrachloroethylene, also known as perchloroethylene, or PERC, is a dry cleaning solvent. We're all familiar with that. Still used in many, many dry cleaners throughout the country, although many dry cleaners are going to more environmentally friendly solvents. PCE is still widely used and very effective. We see it in current dry cleaners, but more importantly, we see it in historic dry cleaners where the processes for handling the solvent were not always the best. Dichloroethylene and vinyl chloride and common degradation or daughter products of TCE and PCE, and carbon tetrachloride and some other compounds such as chloroform are found in common household products. So this is just a sampling of the VOCs that we see on these sites that create vapor intrusion problems. There are many, many, many others, but I would have to say that this grouping probably represents the majority of the ones that we see and have to deal with. So what is the big concern? Another chemical to worry about, but the difficulty is the medium in which this chemical can reach its potential exposure receptor. Before, when we did soil and groundwater investigations, the risk assessment looked at the ingestion of contaminated groundwater or someone coming into direct contact with contaminated soils. We could often predict those or eliminate those exposure routes by providing drinking water, which of course is provided to most modern metropolitan areas, or protecting receptors from contaminated soils. And those approaches were relatively easy or easy to understand and easy to implement. However, with vapors, we have a situation where the chemicals are entering into a structure and actually creating a direct exposure route because individuals in that structure are breathing them every day, thousands of times. So the concern is elevated because that exposure route is very direct, very identifiable, and very quantifiable. And the state has, as you can imagine, very strict guidelines for the quality of air that can be present in residential or commercial structures. So that's why vapor is, in my mind, so much of a concern and will continue to become a great concern because of that direct exposure route. Where do vapors originate? If we have contamination, we know that these chemicals can be absorbed onto the soil matrix. They can be in the unsaturated pore spaces above the water table. And of course they can be in the groundwater and in separate phase product, which is often the source of the vapor that we find is migrating up to the soil mass and into overlying structures. The next graphic shows some of the pathways, again just a conceptual idea of where vapors originate and how they can get into buildings. We see contaminated groundwater or separate phase product at the bottom of the graphic, or soil contaminated with VOCs in the source area. And because these chemicals will volatilize, they are preferentially moved from the saturated zone into the unsaturated, and then have an opportunity to migrate upward into unsaturated soil and then into structures if they're nearby. And those pathways include joints in the concrete, utility lines, cracks, etc. So we'll talk about those in a minute, but this is the typical vapor migration pathway that we're using as our conceptual model for how contaminants get from a contaminated soil or groundwater into a structure. So how do we know if there's a vapor intrusion issue? There's a couple of approaches. One of the The first that comes to mind, if you do have soil or groundwater underneath a building and it's contaminated, can we predict vapor intrusion based upon that data? The answer is we can attempt to do that, but unfortunately the correlations are very poor. It's a very complex system that allows us to model how a contaminant might go from the water phase through the capillary fringe into the overlying soil and into a structure. So it might give an indication that you have a vapor intrusion problem, but the magnitude of that problem is very difficult to model using just soil or groundwater data. Next bullet. A better approach is to look at shallow soil gas concentrations below a building. This obviously is kind of an intermediary point. It shows that contaminants have come from the contaminated soil or water and migrated into the vadose zone and into the soils beneath the slab of the structure. Now we have a much better idea of what is below a structure, and now we can do more accurate modeling of what might enter the structure. But again, this becomes complex because the avenues for that vapor to get into the structure can be very hard to quantify and model because they're vary from site to site. Next bullet. Of course, the best way to know if there's a vapor issue in the building is to take indoor air sampling. And we'll talk about that in a second. Next slide, please, Lance. This slide just shows some of the typical sampling tools that we use if we do want to look at subslab vapors and see if they could enter into a structure, or perhaps if there is an indoor air issue and we're trying to locate the source. This is a vapor pin setup where we can install these small brass pins into a concrete slab through a hole that's cored through the slab and penetrates to the underlying soil. We drive that pin into place, and then we can attach an air sampling Summa canister to the pin, get an air sample, and see what levels of VOCs are present directly beneath the slab. You can see in this situation, this is a modern office building with floor tiles, carpet tiles with glue on them, and it's very easy to peel back some of those tiles to insert our vapor pins, and then when we're done, we put a little stainless steel flush-mounted cover on it and then place the carpet tiles so we can come back and take samples in the future, and it does not intrude or affect in any way the occupants of the structure. Next slide. So air sampling is the best indicator of vapor intrusion. Clearly, if we have contaminants in the air, then we know we have an issue. But often indoor air sampling is completed as a last resort because once we have that data, and if we do have an elevated concentration of one of these chemicals, it can result in notification requirements to the occupants of the building, and because the results can be compared directly to state criteria for air inhalation. So it's the most valuable, but taking those samples sets you down a road that you want to go down carefully to make sure that you know what your obligations are once the data is available, and are ready to notify individuals who could be affected if you in fact do have an indoor air contamination problem. Some comments on indoor air sampling. Even though it is the best data that we have, a number of studies have shown that air quality can vary substantially over time due to season of the year, atmospheric pressure outside, presence of precipitation, which sometimes can reduce the amount of vapor intrusion, and obviously the very complex issues of building construction. And so it's not always a consistent number that you can replicate from time to time. The general industry recommends taking samples over a period of time to get variations in indoor air with season, etc. However, we all know that typical real estate transactions or closure investigations may not have the budget or time to obtain the number of samples that can get us the level of certainty we desire. And in fact, indoor air levels can be affected by background concentrations of chemicals which muddy the air, excuse the pun, and I think the next slide will talk about some of those. These pictures probably look like anyone's cabinet or garage where you have a number of cleaning chemicals, paints, thinners, gasoline for lawnmower equipment or yard maintenance equipment, and of course dry cleaning, which many people use, and if your dry cleaner does use PERC as their cleaning solvent, it's well known that dry cleaning can get inside indoor air in typical residential structures. So here we have a survey question. I think Lance will take it from here. What percent of the time would you expect to find potentially harmful volatile chemicals in the air in a structure? You can select one, then Lance will tabulate the poll and see what the answer is, what the thoughts are of the participants. Okay, I see the poll results are up. So for 10% of the time, I can't see the right side of my screen. Hang on. So for 10% of the time, 11%, 25% of the time, about half the participants, 60% of the time, 22% of the participants, and 80%, 17. Well, if we can go to the next slide, we can show some numbers that have been developed by the EPA that show the percentage of occurrences of contaminants. A study completed in 2011 reviewed 18 different air studies and found that 80% of the time they reported the presence of BTEX compounds in indoor air. And these obviously are commonly associated with gasoline and some petroleum products. Also cigarette smoke, which could be a big factor. I believe benzene is associated with cigarette smokes. And then between 40 and 60% of the time, indoor air sampling, in the absence of other sources, detected chlorinated VOCs, such as the ones we discussed, TCE, PCE, and these other chlorinated organics. So you can see this can really muddy the air when it comes to taking indoor air samples, trying to differentiate what could be a contaminant from an outside source, contaminated soil or groundwater, and an inside source, which would be from common household chemicals such as cleaners, glues, air fresheners, and a number of other common household materials that we use every day. Okay. Dealing with background contaminants, it can be difficult to remove all air sources as part of an indoor air investigation, and so obviously our recommendation is to focus on the chemicals that are found in the subsurface and use those as the ones that are targeted rather than focusing on a broader universe of all chemicals, because undoubtedly you will find a number that you cannot explain based upon the subsurface contamination. Next slide. Okay, now let's get into vapor mitigation. We're going to talk about 4 or 5 approaches to dealing with it. Can you hit the first bullet, Lance? The first one is modifications to an HVAC system, and then identifying and sealing pathways for vapor intrusion into the building, actual treatment of indoor air, subslab depressurization, and then the most comprehensive would be, of course, source treatment, removing the contamination from beneath the structure, which is a kind of a whole other talk. But let's talk about the first 4 principally. Modifying the HVAC system. One of the basic tenets of indoor air or HVAC in modern structures is air exchange rate. The codes for designing air conditioning systems in modern buildings has recommended volumes of air that should be exchanged to keep the air fresh within a building. That is one approach that can be used. The higher the air exchange rate, then the less, essentially the more dilution, you could say, of the contaminants, and so a reduction in the concentration of the VOCs within the air. Next bullet. Isolating rooms overlying affected soil from other portions of the structure. There are situations where a plume might underlie a portion of the building and not another portion, and therefore there might be a vapor intrusion situation in one part of the building that is not in the other. However, when a building has an HVAC system which is interlinked and the air moves across different parts of the building, there have been instances of contaminated air from one part of the building being introduced into the HVAC system and then being distributed throughout other parts of the building. Creating a positive pressure within the building is very effective if it can be accommodated. That is, modifying the air exchange system or the HVAC system such that the pressure of the air using air from outside can be maintained at a very slightly higher pressure than that in the subsurface. And this can be done using careful engineering and modification of input dampers and fans, and it's probably one of the most effective if it can be accommodated with the existing system. And, we'll talk about that more in a second. And finally, modifying fans and exhaust to avoid the development of negative pressures. One of the first things that we all thought about when we talk about vapor intrusion is to essentially vent a building, turn on a fan and exhaust the air within the building. But of course what that does is it creates a negative pressure within the building, and as a result the vapor beneath the slab under a pressure gradient has an opportunity to move into the building. So simply adding exhaust fans is not the answer, but having exhaust fans that can move air from a room while still maintaining a positive pressure in that room is an ideal situation. So that's one of the other HVAC modifications that can be implemented.
Hey, Frank, we have a couple of questions from our audience, if you have a minute.
Sure.
Okay, why is radon and formaldehyde not included in indoor air quality issues?
Well, they are. We're focusing really on indoor air associated with subsurface, man-made subsurface contamination. But radon, as we all know, has been around and known as an issue for decades, and there are very well-established approaches for dealing with radon. EPA has established limits of, I think it's 4 picocuries per liter for indoor air for residential properties. And so if you are in an area of high radon potential, you'll often find someone, especially in residential houses, people will do radon testing and, if necessary, install radon mitigation systems.
Okay.
And in fact, later in the presentation, we've taken advantage of some of the work that's been done on radon to help understand some of the opportunities for venting sub-slab conditions to mitigate vapors getting into a structure. You'll see that a few slides down.
Okay, I do have one more question, actually two, one just came in. So why is vapor, and we might be getting to this in a few more slides, but why is vapor a problem only in winter in some buildings in Texas? I have several clients who have only had an issue in winter.
Right. We do have that as later in the presentation. When they have sampled, there have been some studies done by EPA and other entities where they've looked at homes and they've monitored indoor air quality over multiple seasons. And they have found, I think, consistently that the winter period is the time when indoor air quality is the worst. And I think the principal theory is because of the stack effect. When you're heating a house, you have warm air that is rising and then venting out the building, and when warm air rises, then something must come in to replace it. And so they believe the stack effect is allowing for vapor to enter the building from the subsurface. And of course that warm air is prevalent in the winter when heating systems are running. So it's a phenomenon called the stack effect. I don't know how well understood it is, but it has been documented in many studies that winter is the worst time, and they believe that it has principally to do with that stack effect of heating a building and creating that temperature gradient where warm air rises to the top of the building and air comes in from the bottom to replace it, and that air contains volatile organic compounds from the subsurface.
And then the last question is, I've talked to several people who have found radon problems in the Dallas area. Have you had that issue come up?
We have very seldom do people request radon testing. I think often HUD, if a HUD deal comes along, that they will require it because it's more of a national program. I'd say we've tested maybe only 7 or 8 projects over the past 3 or 4 years for radon because it is not typically required on real estate transactions. We found radon in only one location. All of the others had detectable radon, but not above EPA's guidelines. So I can't explain it because radon, this is considered I think zone 3 or 4, I can't remember the number, but an area of low radon potential. So I don't know why some are having it and others are not, but I would say predominantly we have not seen a radon problem, and we've never had a radon mitigation system that we've worked on in North Texas at least.
Okay, great. Thanks for your questions.
Back to the air exchange rate, there was a study done where they looking at a complex kind of industrial building. They had all different types of rooms and AC systems working on it, and they determined what the air exchange rate was in each of these rooms, and then modified those air exchange rates by doing various things, modifying the dampers within the rooms. In some rooms, for example, that HVAC zone 1 had a very low air exchange rate of 0.01. That was probably a closet or a storeroom that had no active ventilation in it. So it was very easy to see that that was a dormant area where vapors could enter and not have an opportunity to be removed. I believe what they did in a situation like that was to add a small vent fan to that room so that they would have some air exchange rates. So they went from 0.01 to 13 and had a 98% reduction in VOCs measured in that room. And you can read the rest of the table and see similar results, essentially by increasing the air exchange rate, and in this case somehow maintaining slightly positive pressure relative to the subsurface. They had significant reductions in VOC. So depending upon the structure, if there is an opportunity to work with the HVAC system within a reasonable budget without spending a tremendous amount of money, this would be a very attractive first option to mitigate indoor vapor, and if you do have a structure that has an active system that can be modified. Here are some of the difficulties. Building systems can be very complex. If you've ever worked on one or tried to evaluate one, they can be multiple systems serving different areas of the building for different purposes, different air exchange rates depending upon if the area is an office versus a storeroom versus a manufacturing area versus a clean room in a high-tech building. So fine-tuning them to meet the objectives of increasing air exchange rate and still maintaining positive pressure can be a real challenge, and you probably need a very highly qualified HVAC engineer and a lot of field measurements to make that work. But it certainly seems like a worthwhile approach if that can get you where you need to go without significant capital outlay. One other consideration with air exchange systems, sometimes bringing in additional outside air to increase the air exchange rate or to increase the pressure can result in additional costs for heating or cooling that air. And even though it might be a modest cost on a weekly or monthly basis, if that is a system that will stay in place for many years, you could see that the additional cost for that air treatment can add up. So that's one of the things that you would look at, the life cycle costs of modifying the air conditioning system. And in some cases, it may not be a permanent fix. It might be a temporary fix until such time as something to remove the source of contamination can be implemented, which, as we all know, can sometimes take many, many years. Okay, well, here's the question, a question that relates to what the participant question mentioned is, what season of the year would we expect the greatest vapor intrusion? And I think we all know the answer now because it was brought up in the question we just discussed. All right, everyone gets 100 on that pop quiz. So winter is the time when indoor air quality is the worst. Next slide. So sealing of vapor intrusion avenues. We have had a couple of sites where this has been a significant issue, especially on older buildings where you have many maybe cracks in the floor or open construction joints. Can we go back one, Lance? And floor drains, as well as joints between the slab and the perimeter columns. Some buildings have sumps if there's high water, and sumps not only let in vapor, but also sumps, if they intercept contaminated water, will basically provide a direct avenue for contaminated water to enter the building, and then the chemicals can volatilize from that water surface into the structure or into the basement. Utility penetrations are common avenues, especially if they come up vertically to the slab. And in a very interesting situation, we have found that the investigation borings and wells that are put in, if they're put inside a building, let's say you have a large industrial building with the plume beneath the building, and you put in wells to evaluate the extent and concentrations of the plume underneath the slab, we had one particular case where the well casings were by far the most significant contributor to indoor air contamination because the seals around these well casings are often just some bentonite pellets hydrated with water, not a particularly airtight seal, often used to prevent significant water penetration around the well annulus, but not really designed for preventing air migration. So we'll have some slides where we'll show what we had to do in those cases where the actual investigations were creating the problem. Here's some typical pictures of penetrations, cracks in slabs. You can see open floor joints. We often use a PID meter like you see in the upper right to screen joints and sumps and see if we can try to pinpoint avenues where the vapor might be entering. Some of these joints are continuous and might penetrate all the way down to the soil. Some are only open at the surface and they are filled in down below with joint caulk or joint sealing compound. But we use a sensitive PID or photoionization detector that can detect down to 1 part per billion, and it's a very effective tool, and it helps us focus in on the areas of the building where we have the greatest potential for vapor intrusion. Here's some more pictures. Sumps obviously are avenues for vapor intrusion, and in the lower right you can see the wells in that building that I mentioned to you where we had significant vapor intrusion around these wells. Initially we went and tried to seal off the caps by putting in O-rings and rubber seals around the caps for the wells and putting in tight plugs within the well casings themselves, but we found that that was really not effective in preventing the vapors from entering the building. So we've gone to another step beyond that, which I'll show in a few minutes. Here we are sealing some of these pathways. The upper left, you see sealing some of a wide construction joint. This was between a slab and a perimeter foundation wall. And it was probably a quarter of an inch thick, and it had some material in it, but that material didn't appear to be continuous and all the way down to the underlying soil, so we put a construction sealant in that joint. And then in these wells, we used a very specific, highly chemical resistant two-part polymer mixture to seal the annular space around these wells, because we were seeing such significant levels of VOCs coming out of those well casings. So that looks like it's been very effective. We've had pre and post sealing air samples, and the concentrations in the air, at least from the initial round, were reduced by about 80% after we sealed these wells and sealed some of those cracks. One of the third option that we talked about is indoor air treatment. Now, obviously, this is probably not a preferred long-term approach, but it is an approach that can be used to provide some immediate relief from indoor air quality. On the left, we've actually gone and taken carbon impregnated filters. These are the typical filters as you would put in your house air conditioning system. And we've used them within the air conditioning units in this particular light industrial building, which had an office area. And so the carbon within these air filtration units provides some relief and absorption of VOCs that run through the AC units. But on the right, we found some suppliers of air purification systems, which are not too obtrusive. They look good. They look like a house dehumidifier or humidifier. And this particular fan contains about 26 pounds of granular activated carbon, which has capacity to absorb a significant amount of VOCs. And that fan can run up to a rate of over 500 cubic feet per minute. So it can pull in a significant amount of air and significantly treat air that has gotten into a working space. In this particular case, we put the fans in the most actively used rooms, office areas, lunchroom, etc. And again, we saw a significant reduction in VOCs. In this case, it was TCE from levels above the air inhalation standard to about half of the air inhalation standard. So successful as a temporary measure to abate indoor air quality problems in this particular situation. Okay, indoor air quality. Well, here's the question. What do you think would be the typical variation in indoor air quality from the average value over the course of a day? That is from morning to night, based upon temperature, air conditioning systems, doors opening and closing. Do you expect that you would see a variation in indoor air quality from a vapor intrusion scenario? Okay, it looks like the bulk of participants felt that about a 10-time variation would be expected, and 21% thought 100 times variation. And the literature, the reports that I've reviewed, have shown that the 100-time variation is more appropriate, at least in the scenarios that were evaluated. This particular situation was a residential house that had a vapor intrusion problem. The indoor air quality was monitored almost on a continuous basis for an extended period of time. I want to say 18 months or longer. And they had readings every few minutes throughout the day through using gas chromatograph instrumentation. And they found that at the extremes that they had levels over 2 orders of magnitude higher during certain times of the day, certain seasons of the year. Again, it was winter, it was predominantly the worst, than, say, the average concentration that was present in that house. So now these were short-lived spikes often. They didn't last for more than maybe an hour or two. And this is one of the reasons why when we do take indoor air samples, I think it's typically recommended that they be taken over at least an 8-hour period, and perhaps even a 24-hour period would be more appropriate to make sure that you take into account those spikes in air quality when you're looking at kind of long-term exposure. Next slide. The next option, which is a little more intrusive and cost prohibitive, is to do some subslab depressurization, and this simply is reducing the pressure beneath the slab such that it is lower than the pressure within the building, and therefore if the pressure in the building is always higher than in the subslab, then the vapors will not enter the structure. Ideally, this would require some type of pervious layer of gravel or sand beneath the slab that would allow vapors to be transported to a collection point, and then some mechanism for accessing that pervious layer, retrieving the vapors, and then venting those vapors to the atmosphere outside. This is an example of just a very recent project where we did a subslab depressurization system. In this case, we were very fortunate in that the slabs in this particular building was a structural slab, so that is, it was supported with a void space beneath it, and the void space was, I want to say, 12 inches to 18 inches high. It had been formed with carbon construction forms, but those cardboard construction forms, but those construction forms had deteriorated, and so 2 or 3 years after the building was built, there now is a void under this building. So we simply went in, we drilled a horizontal hole into the void space from the side of the foundation wall, and here we are doing a pilot test to determine what flow rates we can get, what concentrations of vapors we're getting out, and how much flow rate is needed to adequately ventilate this space over the long term. And when we are done, we will design and have a fan installed that will be run essentially continuously or semi-continuously to constantly ventilate this space so that it will always remove the vapors from that crawl space before they have an opportunity to enter the structure. We talked about radon, and there's no secret that the radon abatement or radon mitigation industry has provided a lot of very useful information to help come up with solutions, and very practical solutions for dealing with subslab depressurization. The radon sump has become is a common phrase used in the industry, where they have found that just placing a gravel sump in the corner or center of a structure, as long as there's some soil around it that can lead to that sump, and then collecting the vapors, air from that sump, and ventilating them to the outside is a very effective way to get rid of the vapors. And here we show a cross-section with the vapor sump, the pipe going up. They show one exhaust stack going up to the attic, and then they have a second option where you put a small helical pump outside the building with a switch. And again, this is not the prettiest of sights, but not too obtrusive. And if it removes radon from the building and provides comfort to the owners of the structure, then that's the important thing. So the radon mitigation industry has been helpful to get us some options for subslab depressurization that appears to work well. Now in new construction, it's obviously easier if you're building a new building to install a vapor mitigation system. You can put in a heavy-duty barrier, in this case a 30 mil HDPE vapor barrier, and in this case it was placed above a stone layer, 8-inch crushed stone, and piping was placed in that layer, and that piping was run to collection points and headers which can run up into void spaces in the side walls and up to the roof line. Obviously another added expense for new construction, but if you do have a significant vapor issue and you're building in, for example, an urban area like Dallas or Fort Worth, where there are many subsurface plumes that have been historic and we may never know the source, This is a way to deal with them during new construction that is reasonably cost effective, can be built into the cost of the new development, and provide a long-term solution. A little more expensive, but also very good system for dealing with vapor are some of the spray-applied barriers that are available from a couple of manufacturers. These are multi-layer systems which have layers of geotextile with a spray-applied asphaltic membrane. The advantage of these is that if you have multiple penetrations of a slab, like you saw in the last photograph, these spray-applied membranes can be sprayed around those penetrations and therefore provide a good seal. So these are a little more expensive, but have known to be very effective. A multi-layer system, and there's a number of suppliers and contractors who are licensed to do this and to provide a warranty that goes with the system. So that has an added benefit if that's important. And finally, on old structures where you cannot, just sealing the penetrations is not enough, there is a coating that can be applied called retro coat, and I think there's another one, which are chemical resistant and can be applied across wide areas of a floor. This essentially becomes the new wearing surface of the concrete floor, and these have been shown to be effective in also minimizing vapor intrusion into the building. Okay, so to summarize, we've gone through a lot, but I think you've gotten the gist that there are 4 or 5 approaches that can be used, some relatively straightforward and easy using existing equipment, others a little more involved and might require more capital expenditure. But vapor intrusion is becoming a big environmental liability and is a discussion issue on many real estate transactions. The potential presence of vapors and an inhalation risk to occupants of the building may force some short-term measures to abate that risk until a more long-term solution can be identified and implemented. And it's been our experience that sites in historically developed locations are much more likely to have VI issues because there are often plumes from unknown sources located underneath the more urban areas that we may never be able to clean up, and therefore might have to deal with the vapor, assume that they're going to be there and deal with the vapor in our new development. So these vapor mitigation approaches have been established. EPA has a number of papers out that discuss vapor mitigation approaches, and we think that the simple ones should be considered first before embarking on more complex solutions. Using iterative approaches is probably the best way to go about it. See what works initially using the less costly approaches of sealing of joints and vapor intrusion points, or modifying HVAC systems before going on to more expensive systems that are might be necessary to achieve your goal. And I think that's it, Lance. That's it.
All right. Well, thank you, Frank. That was some great information, and it looks like we got some good questions asked. I just want to remind everybody that we are going to be. We did record this, and so we will be putting the recording on our website. I would say probably by 2:30, and then also the slides that Frank used as well. Frank, thank you so much for your time this afternoon, and what a great informational webinar.
Thank you. I hope people got some value on it.
I'm sure they did. And I just want to remind everybody that we do have an upcoming webinar on hazardous waste management training on August 18th, as well as the SPCC plans, the 5-year updates that are going to be due here really soon. So, and you can get signed up for that on our website under the events tab. So thank you guys for joining us, and I hope you guys have a great day. See you soon.